forgot it was in this room, didn't you?
Yeah, I did.
No surprise. All right.
I was like, they'll be here in a minute now.
For this condition, it's easy to show that the vector potential is 1/2 V cross R, where R in the particular coordinate system under investigation. Let's do an example to make sure we understand this. All right, let's take as our example, there's some book examples, but I like this example. Because this is one you see, and this is relevant, you see a lot in the books and on the comprehensive type exams. But even more importantly, this is the one right now that is under, let me get this from the beginning. If you walk down to the mag lab, or you pick up a physical review B, which is condensed matter, and you look in there, they talk about blah, 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 blah in a magnetic field. Generally, for whatever reason, and I'm no experimentalist, they always tend to put the magnetic field along the z-axis. Usually, there's some sample down here, and then there's wires. You can see that I'm a theorist. There's a sample and there's wires, okay? And they put the magnetic field up through here. And one of the reasons they do that is, I'll show you in a second when we get to materials, but one of the reasons they do that is it's simple and it simplifies the mathematics of any kind of model you want to make. So what is the vector potential appropriate to a magnetic field in the z direction? This would be 1/2 B naught K hat, and because this is in the z direction, and most of the time things will have some sort of symmetry, cylindrical symmetry, I'm going to go ahead and say, look, let's call that R rho hat. So any place I go, it'll be rho hat here. So that'll be cross rho hat, and we'll have 1/2 B naught, and then I'll have K cross rho is D hat. I think K cross rho is plus D hat. Okay?
Yeah.
All right. And of course, R has its own rho. I should put that first probably, and that looks like this. And of course, not of course, I shouldn't say of course. It's of course after you've done it a million times. The vector potential forms loops around here in the phi hat direction. So the vector potential is azimuthal, here's A, and it goes as you get further out. And if you want to plot that, it looks like this. Interestingly, it can be around any origin you want.
So where did you get, I understood when you talked about the sample and the thing on us, and then you just picked an R like anywhere and started drawing.
R is measured from the origin.
Okay.
R's
On your sample.
R is right here.
Yeah.
You don't need a sample though. Okay? R in cylindrical coordinates is rho hat plus z k hat. What's k hat cross k hat? Alright, so I only need the rho hat. Okay, and there it is. Cylindrical coordinates work very well for things when they have an orientation along the z direction. For a single magnetic monopole, for a single magnetic dipole, we can find what A is from B. Let's do that very quickly. I know B from a monopole. I keep saying monopole. Edit that out.
Dipole.
Okay, dipole. Mu naught over 4 pi.
But there is no monopole.
There are no monopoles. This is 3.3 R hat dot M. This is R hat here, right? Minus M over R, and that's it. The R cubed I put over here. Did I make a mistake?
No.
Okay. We remember that, right?
Yeah.
So I already know then that I have a sneaking suspicion that 1/2 doesn't belong there. Maybe it does. All right. I don't know. U naught over 4 pi, and then I will do B cross R. Will be the A appropriate for a single dipole, and that's what we'll be needing here in a minute. B cross R will give me 1/2 mu naught over 4 pi, and then I'll have, let's see. Well, look, let's make this a little bit simple. R, if I were to multiply by R over here and divide by R, what's R cross R?
R vector over R.
What?
0.
Oh,
Kevin, you are
I
so.
was thinking of something else.
I'm afraid I'm going to have to turn my back.
No.
no, turn it back.
I was thinking of R hat.
Oh, he actually showed us a clip of it yesterday.
Let that be a lesson. All right?
Stupid brain.
So, this is it. all getting taped. It'll be an ugly development. Or, is that you?
Yes.
What is it?
My boyfriend.
Some weird 871 and 872.
His
I'm
mom
checking to
was
see
dragged to the shopping.
one half. Oh, gosh, yeah.
It's just history to make some.
For some reason, my one half isn't there. I'm looking at something. Boy, this must be good.
Where they're peanuts.
Well, whatever. It turns out to be, for whatever reason I have,
There is no one half.
there's no one half, there's no one. It comes out to be this. The important thing is this M cross R. Okay? That's what's important. Now we're going to move on, and that's it for chapter 8. We want to move on to magnetism and matter, which is chapter 9. We need the result of this M cross R, and I never get any of those constants right because I don't work in that system of units. But A is then J, something proportional to J, and we'll just use currents mostly, I dl over R. Okay? And we talked about this last time, that A is good because it's in the same direction as the current. What are we going to do with this? Well, a lot. A lot. The first thing we want to talk about is magnetism and matter requires matter. So I'll have a slab of it. Here it is. Now, when we did electrostatics and we did dielectrics, I put a bunch of little dipoles in here. And then I said, look, let's draw a volume out there, really small.
Oh.
You remember that? Really small. In fact, I can still remember how small it was. It was a micrometer on a side. It was 10 to the, I think it was a micrometer on a side. So, yes, it was. Yes, it was. It was a micrometer on a side. And then we found out, even if we looked at a little micrometer on a side, we had on the order of 10 to the power 18th dipoles in there. And that allows us to do good averaging. Because when you have a billion of something, the fluctuations tend to wash out, right? The fluctuations tend to wash out. And you have a well-defined vector. And the way we did that was say, look, let's get a dipole moment per unit volume. I invested all this emotional.
You got really excited.
I got really excited about it. I got all emotional about how well this pen was working. And now it's letting me down. P is equal to 1 over however that delta P was, sum over all the little dipoles in there
What does
around
P
some
do?
point.